Now we're going to introduce mathematical induction, which is another way of proving things. We're going to see, though, that the way it works is quite different than what we've seen up till now. So recall that we saw this sum in a previous video. And so once again, this says 1 plus 2 plus 3 plus ... plus n could be, the sum here could be produced by simply using this formula. And we saw what I would consider a direct proof of that allegedly was created by the mathematician Gauss. Okay? But for these types of problems, mathematical induction is typically the way it would be proven. And so let's note a couple of things before we see how that works. Why is this a case for using mathematical induction? Well, mathematical induction is used for things that can be tied or associated with, so tied to the natural numbers. How's that work here? Well, if I were to say, and we'll see this in a moment here, P of 1 is simply just the first number. And so the sum is 1. And then P of 2 is equal to 1 plus 2. And the sum is 3. P of 3 is equal to 1 plus 2 plus 3, which is 6. If this instead was 1 plus 4 plus 5 plus 18 plus 93, unless there's some way of associating that with the natural numbers, I wouldn't be able to use this. Because when we say associate with the natural numbers, it doesn't have to be this obvious. It could have been something like this. 1 squared plus 2 squared plus 3 squared plus ... plus n squared, right? There's the associated with the natural numbers. We could have problems like this. We won't do any of these proofs. But there are things like this where maybe you see something shaped like this. And you say, well, okay, I can do something with this, where this is, say, 2 by 2. And then the next size is 3 by 3. The next size is 4 by 4, and so forth. Now, we didn't start at 1, although you could, depending on the problem. So this would be 1 by 1, 2 by 2. See how these are growing by 1 each time. So that's the deal. These are growing or changing by 1 on each in each case. Now there is a downside though to mathematical induction. That is, when we looked at things involving logic, we saw that we could actually discover new things. So we might have something like this. Well, we know that A implies B, and we know that B implies C, and C implies D. And so given A, we actually know that A in turn ultimately gets us down to D, right? We sort of stumbled into things. In terms of mathematical induction, where does this formula come from? Well, we can't just be doing things like this, and mathematical induction doesn't spit out a formula. It simply verifies the formula. Okay? So you still had to have had some way of coming up with this, which is what the mathematician Gauss did. Remember, because we had 1 over here plus 2 plus ... Down here we have n plus n minus 1. Remember, that's what he did, allegedly. And saw that this is 1 plus n, 2 plus n minus 1 is really 1 plus n, 3 plus n minus 2 is really 1 plus n, and so forth, right? So you still have to have some way of coming up with the formula on your own, and then you can use induction and try to verify it. Okay? So what does mathematical induction tell us? Well, there's different versions of it, but we're going to look first at what we would call the first principle of mathematical induction. And it says in logic terms that given P of 1 and for all K, P of K implies P of K plus 1, that this implies for all n, P of n. So what does that mean in English? Well, it says that if P of 1 is true, and for all k, P of k being true implies P of k plus 1 is true, then P of n is true for all positive integers n. So basically we're building things up. We show P of 1 is true, and let's put a little star on here because strictly speaking it's not always 1, but that's what you'll see typically in the textbook examples. But you have to have something to get the process started. And so then we know if the next thing is always true, well then P of 1 is true, then means if the next thing is true that P of 2 has to be true. And so if P of 2 is true, then the next thing after that is P of 3, so that's why we know P of 3 is true, and so forth. Right? This will make a little more sense as we work through it. So how do we actually do it? At least in this case. And it will look like some magic is happening as well. Right? So typically we do this. Show that what's called the basis step P of 1, and once again a little star there to indicate could be P of 0, could be P of 10, depends on your problem, but this is the standard way you see it. You'll see examples for which this will be what you really would use. The base step P of 1 is true, and we have to actually show this. Then 2, we assume that P of k is true. And 3, prove P of k plus 1 is true. And we do that using what's called the inductive step. That's P of k implies P of k plus 1. Okay? So let's go back to our earlier example and see that. So we'll work this out and then we'll explain it. So first step, basis step, P of 1. So remember we're working with this. 1 plus 2 plus 3 plus ... plus n is equal to n over n plus 1 divided by 2. So P of 1 says, now we have two different parts here, right? This side assumes we don't know the formula. This is just the summation here. Okay? So no formula. And this is the formula side. So what's P of 1? Well, if n is 1, it's just the first number. So I just simply said 1 plus nothing else. But the formula side says n is equal to 1. So the formula side is 1 times 1 plus 1 over 2, which is 1 times 2 over 2, which is 1. 1 and 1. So I produced the sum. If we only had a single number, that was 1. I produced the sum using the formula, which also was 1. Right? So now we assume that P of k is true, which means we would have 1 plus 2 plus ... plus k, the kth value. And if that's true, then according to the formula, and I'm replacing each n by k, we'd have k times k plus 1 divided by 2. We assume that's true. But now we're going to put it to use. So let's look at something. What is P of k plus 1 then? P of k plus 1, and this part we do know to be true, would have to be 1 plus 2 plus ... plus k, k plus 1 is the next higher number, right? It grew by 1 here. So the next higher number here is k plus 1. That part's true. If I'm summing the first k plus 1 numbers, it has to be 1 plus 2 plus dot 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 up to k plus 1, because this is 1 less than this. This part absolutely has to be true because this is a summation we're given. But the formula side says that, now I replace each n by k plus 1. The formula says the summation is k plus 1 times k plus 1 plus 1 all over 2, according to the formula. We don't know if this is true yet. This is simply the sum of the first k plus 1 numbers. But here's where the magic happens. What do we have right here? 1 plus 2 plus dot 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 down to k. So imagine k was 3. Then we would have 1 plus 2 plus 3. So therefore p of 3 plus 1, which is 4, would be 1 plus 2 plus 3 plus 4, right? Well, if the formula is really true, then I can replace this part by the formula. This right here is really just p of k. So it says p of k plus 1 is equal to p of k plus the extra value, k plus 1. So let's use the formula in this place. If I still just add these up manually, it absolutely has to be whatever the correct sum is, unless I make an arithmetic mistake. But we're assuming this formula is true, and if that's the case, I can replace my hand-calculated summation with this formula. So that means p of k plus 1 plus k plus 1, this value right here, is equal to k times k plus 1 divided by 2 plus k plus 1. And let's go ahead and scale this up to save some room here. So if this number divided by 2, so I'm going to divide this by 2. So k plus 1 times 2, I wrote over here since I had room, times 2. I'm just multiplying by 2 over 2, right? So this gives me k squared plus k plus 2k plus 2 all over 2. And this simplifies to k squared plus 3k plus 2 divided by 2. Assuming this formula is correct. Right? Here we use the formula directly to get p of k plus 1. So let's see what this simplifies to. So this right here becomes k plus 1 times k plus 1 plus 1 is really k plus 2 all over 2. And this becomes k squared plus 2k plus 1k plus 2 over 2. And now we simplify this. We get k squared plus 3k plus 2 over 2. K squared plus 3k plus 2 over 2. K squared plus 3k plus 2 over 2. These are the same. And therefore, we've shown by mathematical induction that this formula here really does produce the sum of these n values. Okay? So once again, what's really happening here? Start with the basis step. This is something that gets us going. We show it's true for at least a first value. We assume this formula is true. And then we use our assumption to produce part of this summation and then simply add the difference to it. And then over here, we use the formula for the entire sum of the k plus 1 values. And then we show the two sides are equal. If any part of this is wrong, then we shouldn't get the same final result here. But anyway, that's the basis, or that's the basic form of mathematical induction.